Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. Today I will continue what we started yesterday, meaning that we look into distributed file systems. So in essence, how do we reconstruct a hard drive as you know it from your laptop, but on a cluster of machines with, let's say, 1,000 machines? As you can imagine, we're going to be able to store much more data than we can on a single hard drive. But it's not only about that, it's also about parallelizing, meaning that we will be able to access the data in parallel on all of these machines. So it's not just that we improve capacity, it's also that we improve throughput. And I insisted on the fact that we improve throughput is fundamental for distributed file systems, right? I told you yesterday, if your problem is the CPU and your CPU is overloaded on your laptop, the solution is not to use HDFS or MapReduce or Spark. The solution is high-performance computing, HPC, which is a whole different technology, right? If the problem is the network bandwidth, then the solution would be to download the data set locally, right? So it's other solutions. But if your problem on your machine is that you cannot read from the disk fast enough, then HDFS and what we will see in this lecture is the solution. So, okay, I think it didn't load the right set of slides. Let me just load the correct one, which I think is this one, just to make sure we take it from exactly where we were. All right, so we finished yesterday with the blocks, the size of the blocks. And I explained to you the intuition of why in HDFS, typically the size of a block is around 128 megabytes. It's the order of magnitude that is important, right? It's the fact that it's hundreds of megabytes and maybe also a few gigabytes nowadays that some providers start doing this. But not things like kilobytes, that's too small, and not things like terabytes or petabytes, that's too big, right? So this is kind of where we are with HDFS. So as you can see, a block is much bigger than it is on your local hard drive. All right, and we'll develop the intuition of that with time. So let's look at the architecture now. How are we going to connect all of these machines together that we have in our cluster? Well, we already saw this and last week that we could connect the machines like this, right? It's called peer-to-peer architecture. In fact, this is what key-value stores do. Dynamo connects the machines like this. It might surprise you because I drew a ring, right? This circle, but the circle was only a logical thing. It was only the representation for the responsibility of the keys, right? But in fact, in Dynamo and in distributed hash table, any machine connects to any machine. This gossip protocol that I told you about in order to broadcast the preference lists and make sure they all have more or less the same is based on the fact that everybody talks to everybody, right? So, but in our case, this is what we are going to have. And for many technologies, it's a centralized architecture where we have some coordinator nodes that is kind of centralizing everything. And then we have worker nodes. There's plenty of different terminology you'll find in literature. So I put a few here just so you're not surprised. I'm probably going to call that coordinator nodes and worker nodes or primary, secondary, we'll see. But just be prepared to see many different words in the literature. All right. So now I'm going to give you the more precise names. The coordinator node, we are going to call it a name node. You might sometimes see name nodes written in this way with just an uppercase N, but you might also see it in camel case. Just like Java classes, you're probably used to this. So capital N name and capital N nodes pasted together. It's just because that's the name of the Java class in the implementation of HDFS, which is in Java. So you might see the camel case. All right. And the worker nodes, we call them the data nodes. And it might not surprise you that the data is stored on the data nodes. Exactly. There's no data on the name node. It's all on the data nodes. All right. I also put a few blocks in there just to show that this is where the blocks are on the data nodes. Now it doesn't do justice to the system because I only have 3 blocks drawn in here. But if you do the math and you divide the capacity of a hard drive, like a few terabytes, divided by 128 megabytes, so the size of a block, you'll see that it's more like a few thousands of blocks that you're gonna have on each machine. I was not going to draw 8,000 blocks on my PowerPoint slides, obviously. All right. Now, how do we store a file on HDFS? Right. Remember, we call them files. In S3, we call them objects. Here, I call them files. So we have a file. The file is going to be, I'm looking for the verb because there's 10 different verbs to do that, but let's say split into many blocks. Somebody asked the question yesterday. It's a very good question. Can we control how the blocks are split? The answer is no. It is exactly 128 megabytes. Right? As soon as you have 128 megabytes, you cut it there, and this is your next block. It is an exact size for the block, except for the last block, which might be smaller. That's the only exception. Now, the fact that the last block could be smaller is a difference with your local hard drive, because in your local hard drive, the blocks must be all 4 kilobytes, right? You would probably pad with zeros. In the case of HDFS, the last block can really be smaller, and I will explain later why that actually is, right? So all the blocks, n-1 blocks with exactly 128 megabytes, and then the last block that can be smaller than that. So we do that. We divide it into 120 megabytes blocks. Chunks would be the Google file system terminology. I'm trying to get you used to these different words. And what do we do with these blocks? We spread them all over the cluster, right? In fact, we not only spread them all over the cluster, we even replicate them. Remember, replication, that's how you ensure fault tolerance, right? We already saw in the case of Dynamo that we replicated the values multiple times. And here we do the same. We store every block several times. By default, it's 3 times, but you can change it. If you want it 5 times or 10 times to be absolutely sure, you can do that. And so we store 3 copies of each blocks by default on the cluster, and we just spread that all over the place. So if I have 10 logical blocks in my file, 10, then I'm going to be storing 30 physical blocks, right? 10 times 3 for the replication, all right? And again, that's for fault tolerance, because imagine that, I don't know, this server crashes, this node crashes, you still have a copy here and a copy here, right? So this is the reason. Now, something that is important is that these 3 replicas of my block, they are not in any particular order. There is no such thing as a main replica and then the other replicas are secondary. That doesn't exist. It's just 3 replicas and that's it. No particular order. I see a very good question in the Zoom chat, Martin.
What if the name code crashes?
Yeah, what happens if the name node crashes? And indeed, you identified the single point of failure of the system, which is the name node. What if it crashes? I'm just going to make a cliffhanger on that, because I'll come back to that. I have slides on exactly this, how we actually solve that problem of the crashing of the name node. So I will give you an answer shortly. Well, it did not answer your question, but I'm basically saying I will answer your question because I have slides for that, right? I really like that because, so this question and also many of the questions that you asked yesterday, I'm very happy about them because these are all questions that are basically about what's about to come. So it means you're exactly asking the right questions. It means you understand what's going on.
One more question, is HDFS placement aware for the replication?
Yes, absolutely. When we place, I will also have a few slides to explain how we place the blocks on the cluster. There are algorithms and strategies for deciding where you place the replicas, right? So that also I will answer in this lecture. Any more questions before we proceed? All right. So logically, it's very easy. We have a hierarchy of files organized in directories. Each file is divided into blocks. We take the blocks, replicate them 3 times, and then we spread the blocks over the cluster. Think of it randomly at this point, just a random distribution over the cluster. All right. And now we have the clients of HDFS. So these are the users that want to store files in there and retrieve files, read them. the idea is that they can all connect concurrently, and it usually starts with the name node, right? They first connect to the name node for the meta aspects of the query, and then they will connect for the data to the data nodes for the data, right? Now, what could be misleading in this picture, and that's also something that will become clearer later, is that here the picture makes it seem like the clients are outside. And indeed, they could be outside. Like, imagine that the name node and the data node, this is in the data center in Amazon or Azure or Google. And these computers here could be your laptops, right? You could connect with your laptop, you have HDFS installed, and then you connect to the name node and do things. So it works. In fact, you can do it, but it's not the most efficient way of connecting to a HDFS. In fact, what happens most of the time is that these clients that are right here, these are in fact also nodes in the data center. These are other machines in the data center that connect here. Now I'm going to push it even more, and I will even say that these clients might actually be processes running on these same machines. Like this here could be a client, right? This node could be a client. This node could be a client, right? So these nodes here can both be data nodes and clients, which gives me the opportunity to clarify that we use something that's called, I can't remember, it's a figure of speech. I'll look for it. The idea is that we tend to call the machines data nodes. Like this machine is a data node, this machine is a name node. In fact, it would be more accurate to say it's a process running on the machine, right? The name node is a process that runs on some server, and the data nodes are also processes running on some server. So on these 6 servers right there, you will have the data node process, but you might have some other process that could be anything, right? Could be any other application that itself is a client of HDFS, right? It's just, you know, that you can have several processes on the machines, right? And it will add up because we'll see the processes later. In fact, it's like MapReduce, Spark, and so on, which will connect to HDFS. All right, does it make sense? Okay, yes, we have a question here. Does it actually work with the batteries? Yeah. Yeah. Go ahead.
So we only have one data node process, each,
yes,
and one name node process, and it cannot be like a name node process and a data node process on one machine.
You got it right, exactly. Okay. So you have at most one data node process per machine, and you will not have typically a name node process and a data node process on the same machine, right? These are really different machines. So this is absolutely correct. I'm pretty sure that if you really try, you would manage to put the data node process on the same machine as the name node, but that's not the intent. It wasn't designed to do it that way. So we really have 7 machines here. There is exactly one data node process on every machine except one, and in that one that doesn't have a data node, we have the name node process. Okay? It's exactly as is drawn here. Right? The only machines that could be the same are the client machines and the data node machines, or even the name node. All right. It's all done in Java. That's why the camel case. And it's actually also possible to access HDFS with Java. So you have plenty of ways, but that shouldn't be new to you, because I explained last week that for many systems, you can access them from the shell. There are commands from the shell that you can use. You can access them programmatically from a specific language. You can access via a REST API, and there is a REST API for HDFS as well. So you see there are plenty of question. Yeah.
If data nodes are processes on a server, is the block of 128 megabytes data actually stored in smaller OS compliant 4 kilobyte blocks?
I didn't get the end. It does the Darth Vader voice against the microphone. Let me directly see. If data nodes are processes on a server, is the block of 128 megabyte data actually stored in smaller OS compliant 4 kilobyte blocks? You're already asking about the physical level, which I will also cover. It's an excellent question. In fact, remember data independence, logical layer, physical layer. On the logical layer of HDFS, we have these 128 megabyte blocks. On the physical layer, we'll see that these blocks are actually files on the local machines. So if you take Like let's say the green block here on the left, it's a file on the local hard drive on the machine running the data node process. It's a file. And then, of course, physically, as a file on the local hard drive, this HDFS block will itself be stored physically as 4 kilobyte blocks, right? Physically. But as an HDFS user, I don't see that. It's all hidden. But you got it correct that in the end, these blocks are themselves stored in physical blocks of 4 kilobytes on a local hard drive. Did it answer your question? Yes, awesome. And this was a very good question. It's exactly the right thinking of thinking at all these levels of abstraction. The user sees the node. So all you see here is exposed to the user. The user of HDFS knows about the data node, about the name node, about the blocks. The user sees that, right? And in the API, in Java, it exposes the blocks. It's important because later we will want to run in parallel. So seeing the blocks is what allows us to run in parallel, right? But what we do not see is the 4 kilobyte physical blocks in here. These are hidden, nicely hidden by the API, right? So you see this concept of data independence, it's not only for relational databases, it also applies in that case, right? Okay, so now I'm going to dive into these components to be even more precise and look inside on what we have. I'll start with the name node and then we'll deal with the data nodes. So what do we have in the name node? Well, what you already know is that what we surely do not have is data, right? There is no data in there, but there is metadata. So the first thing we have is the file namespace. This hierarchy of files and directories is stored on the name node, but only the hierarchy, not the data itself, right? Just the names of the directories and files and the tree structure. And indeed, you understood correctly, it's all on the same machine. So this puts a constraint on the size of the namespace, right? The size of that namespace must fit on that machine. This is the reason why it's smaller than the number of objects you could have on S3, right? So there's this idea that if you have a completely flat list of key values, as in cloud storage, you can use distributed hash tables and technologies like that to scale out. But if you have a file hierarchy like in here, the hierarchy is on the same machine, so it constrains the number of files you can have, right? So a few millions maybe, but billions would probably be more difficult to fit. The second thing we have, because that was the first, file namespace. Oh, plus access control. You might also have some POSIX-like way of assigning users and groups and authorizing users to read and write. That's just very similar to your local hard drive. Then we have a file to block mapping. So it means that for every single file that is a leaf in the tree that you have on the left, every file is mapped to blocks. But not the actual blocks, right? Because these are on the data nodes, to block IDs, right? So every name of a file, every path to a file is mapped to a list of block IDs, right? And these are actual paths here, right? It's not just the slashes like in S3 that are virtually interpreted in the UI. This is an actual path, all right? So file to block IDs, list of block IDs. And the third thing that I have on the name node is a mapping from each block ID to the IP addresses, let's say, of the data nodes that have a replica of it. So if it's in cruise mode and I have 3 replicas of each block, then every block ID here is going to be mapped to 3 IP addresses for the data nodes that have a replica. Here it's just smaller on the side, so I have only 2, only 1, but think of 3 every time, right? And again, it makes sense, the IP address, because as you correctly noted, there is one data node process for every machine. So if you have the IP address, that's sufficient to identify the data node process. All right. So this is it. These are the 3 things we have on the name node. For whom does that make sense? Who agrees that this is sufficient to reconstitute logically the whole file system, including the data, right? This is enough. If I give you a file, like a path to a file, you can look it up in the file namespace, you can check the access control, you can get the list of block IDs, and then you even know where to get the blocks themselves. So you have all the information you need in there. Do we have a comment on Zoom?
Can files become so big? node will not have enough space to store block locations?
Yes, absolutely. And indeed, that puts a constraint. If you start putting so much data in there that you are storing billions and billions of files, at some point it's going to break. Absolutely. It has its limits. And the limit is basically the size of the file namespace, which is constrained by the fact that it has to fit on one machine. Right? Does that answer your question? We'll assume yes. Okay. So this is the name node, right? Not so complicated. Now let's go to the data nodes that have the actual data. In fact, this is it. That's what a data node has. It seems actually boring. It just has like, let's say 10,000 blocks. These 10,000 blocks technically are 10,000 files on the local disk of the machine running the data node. These are actually files physically, right? On the local disk of the machine. And then, of course, physically, you have all of this architecture with the inodes and all the things you learned in the computer architecture courses. That's on a single machine, but it's orthogonal to what we are discussing because since we are talking on a higher level, I don't need to go into the details of that, right? Okay. Now, what's really nice is that since the data node process is running on some machine that has a hard drive, it can also detect if the hard drive has a problem by communicating with the system of the machine. So each data node can notice and report that there is a problem with the hard drive, meaning that it has corrupted blocks or physical blocks that cause a problem, and then it can inform the name node about this, and then you can just consider that the hard drive is unusable and stop using it, right? All right, and even if it crashes, it's not a problem because we would have copies somewhere else. So at some point, maybe the disk crashes on that very data node, and there are two other copies. What's going to happen is that the name node will then be informed of that. It will know that there's only two copies left of that block. It's called under-replicated. And then the name node is going to instruct that a third copy is made again to some other place, right? Every time it's under-replicated, you make new copies and re-put them somewhere else in the cluster to always have this goal of 3 replicas for each block, right? What are the block IDs? It's just a long, if you know what a long in the programming language is, right? It's a 46-bit, 46, that's my German coming here again. So 64-bit integers like this that identifies a block, right? And these block IDs, this is what we have in this mapping right there. These are the 64 long integers. All right. Now, it is also possible technically, so you can request the entire block. If you have this 64-bit integer, you can say, give me the block, give me the 128 megabytes worth of data stored in here. The API also allows you to request part of a block. You can also say, I don't want the entire block. I only want like from here to here in the block. Now you could tell me, but that sounds like random access, right? Because now I can just connect to any, to the name node, ask for a file, and then randomly access a specific block, requesting specific bytes in there. Yes, absolutely. You can absolutely use it for random access. But as I said yesterday, if you want to do random access and shuffle the entire file, it's going to take you 30 years to go through that, right? So just because you can do random access doesn't mean that it's a good idea, doesn't mean that it's a good idea to do that. However, the reason why we are doing that will become clearer when we study MapReduce, because once in a while, it's rather rare, but once in a while, we might need that to only access part of a block and not the entire block, which means a bit less data transmitted over the network, right? But this has to remain an exception, and usually you read the entire blocks in there. Does it make sense? Who is following? Okay, who is following on Zoom? Raise your hand. Because we have 70 people on Zoom, right? Are you following? Raise your hands. Yes?
Yeah, they're raising.
Plenty of raised hands. Okay, so we have everybody with us. Okay. Okay, so now we know what there is on the name node. We know what there is on the data nodes. So the next thing we need to look at is how they communicate with each other, how this whole thing orchestrates. This is the overview of things. So of course I simplified, right? I only put, so there's only one name node, but I only put 2 data nodes in there. Imagine that there are 10,000 of them, the data nodes. I only put 2 in here. So over the network, you need to distinguish between 2 kinds of connections. There are the connections where the data is actually transmitted. So the blocks actually flow through this from the data node to the client. Yes, go ahead.
Is name node also backed up?
Yes, and there are also slides. You are really awesome because that's exactly the right questions of what's going to follow. Yeah, so that's an excellent question. And yes, indeed, we'll have backups of the name nodes, right? And I explain exactly how this is done. All right, but you have exactly the right thinking. You know, it's like you're reasoning like the engineers of HDFS, which is great because you might be the future engineers that are going to design the next systems, right? So it's the right mindset. So we have the data. So the actual blocks, they only flow here. You will never see any blocks going through the name node, right? It's only between the data nodes and the client. But there are other connections in here that I call control connections. There's no data, but there is still, they speak with each other, right? So there is still a bit of communication going on here and also here between the data nodes and the clients. I'm just going to dive into each one of these. So this is just the same thing, but now I give the name of the actual protocols that are used. So we have the client protocol between the client and the name node. We have the data node protocol, that is the communication between the data node and the name node. We have the data transfer protocol, that is the communication through the client and data nodes. And as part of the data transfer protocol, we have something called a replication pipeline, which is a specific implementation of the way we are copying the blocks. And I'll go into the details of that now. Now we have a question.
Yeah, we have a very long question. So you might want to read it because it cut me. So when a disk crashes, what's the keep source on which disk? I assume the name node doesn't know which ID, which particular disk of any node. Store a list of IDs per the name node know which block IDs to replicate again.
Mm-hmm. So in the simple case, let's assume for simplicity, there is one disk on every data node, just for simplicity. The name node has this mapping from file to block IDs, and it has the mapping from the block IDs to the data nodes, right? So it knows, the name node knows which data node has a copy of which block. Now, what if the data node has, let's say, 3 disks? That's possible, right? You could connect multiple disks on the same physical machine. So imagine that here you have 3 disks instead of just 1. What's going to happen is like 5 disks in there. What's going to happen is that if that disk is broken, then we lose of course the blocks, and the data node is going to report that it lost some of the blocks, but the data node still has 4 working disks, right? So it's not like the whole data node is broken. It's only that some of the blocks got corrupted and cannot be accessed anymore. And what happens then is that once the name node knows that on this data node some of the blocks were lost, the name node doesn't know which disk it is. It doesn't need to know that, right? But the name node is going to then instruct that a third replica is made again to bring it back to 3. It is possible that the instruction to create a third replica arrives again on that same data node, and that, for example, the block that was lost on this machine right there, actually a copy is made from somewhere else, and then you recreate a copy here. That is a possibility. But it could be another data node, right? It could be that this data node doesn't receive an instruction to make a copy, and it's some other data node that's going to create the third one, right? So anything is possible because this is decided on an upper level. Did this answer your question on Zoom? Who knows? Oh, it's the data node that knows that. So the data node knows which block IDs are on each disk, and it monitors things, and it will notice. You can imagine, for example, if the disk crashes, if it scans, it can, looking at just the metadata of the files, it's easy to see what the list of the files is, right? And then it will notice that some of the files, some of the blocks can no longer be read, and then it will know that these block IDs are no longer You can no longer find them. Right. This sort of scan is also what backup software does, right? When you do a backup, it scans your file system and does the list. Yes, go ahead.
In the framework before, we said that the name node has all the data, and the data node has all the meta information, and the data node only stores the blocks. So shouldn't the name node actually make a request, and then the data node throws an exception, and the name node should somehow recognize, okay, we have an exception here, replicate the data again.
That would be an alternate design to do it in that way. The problem with this design is that it would overload the system because there would be too many requests constantly going over the network. So the idea is really to decentralize things, and the data node, what I mean on this slide right here is that it's the data node's responsibility to detect the blocks that it has lost, right? It's really something delegated to the data node. So the name node knows what data nodes have a copy of the blocks, but the name node does not know which disks, right? The disk is a detail of the data node that the name node doesn't know about, right? From the perspective of the name node, it could be just a single disk per machine, right? It doesn't even know if there are multiple disks, right? Does it make sense? Yes, we have two other questions right there. I think you were first. Yes, this is correct. I think maybe I should have put it on the slide, but the data node has somewhere some list of the blocks that it was. In fact, I will. It's part of what I'm about to say because there's a few slides on that. What happens, in fact, the way that these things are done is that every couple of hours, the data node is going to scan the file system and send what is called a block report to the name node. So every 6 hours or something, the data node will say, these are all the blocks I have. And then the name node will know which of the blocks are missing, right? So every couple of hours. I assume that, so these are probably details, maybe the engineers thought of that, but if there is a real crash and the data node already knows there is a crash, maybe they have some way of not waiting for 6 hours, but of already telling the name node that there is a problem, right? But this would be already contingency things. Does it make sense? Right, and I will explain these block reports, how it all works, the communication. You also had a question, I think you or, yes? I already answered, okay, wonderful. Okay, it means that was a good question. All right, so now, application pipeline, yes. So let's do them one by one. The communication between the client and the name node, it's RPC, remote procedure call. And it's basically the client saying, I want to read a file, write a file, and so on. And then the name node says, yes, of course. And these are all the block IDs, and these are all the locations of the blocks, right, in Java. Then there is the data node protocol. The data node protocol is between the name node and the data node. Now, what happens is that it's a client server, but be careful because it's the opposite of what you might think. You might think that it's the name node that connects to the data node, but actually it's the opposite because otherwise it would be too many. So it's the data nodes that periodically connect to the name node. In fact, every 3 seconds, they connect to the name node, and that's called the heartbeat. Every 3 seconds, it's, I'm still here. I'm still here. I'm still here. And it goes on and on like that, right? And of course, if at some point the name node notices that it's missing some heartbeats, then it will know that maybe the entire name node has crashed, right? And then it will consider that the blocks are gone and they are under-replicated and then make copies somewhere else. This is a heartbeat. The registration means there's a new node that joins the cluster and it registers itself with the name node. Of course, it's empty. Then it might get some new blocks. The block reports, that's every 6 hours. It's this full list of blocks based on the scan of the disk that the data node has. And that way, the name node can update its mappings thanks to the block report every 6 hours. And there is also a way of saying that you receive the block, but that's part of when you write. I'll have slides on that. The data node can confirm that it received a copy of some block. Now, the fact that it's always the data node that initiates the connection does not mean that the name node cannot do anything with the data node. On the contrary, the name node can give instructions to the data node. It can give the instruction, create a replica of that block that you can copy from that other machine, for example. So it can give instructions. But whenever the name node wants to do that, it has to wait for at most 3 seconds for the next heartbeat, and then as a response to the heartbeat, give the instructions. This is how it works. So I hope it's all coming into place now, how this thing works. Mm-hmm.
So in case of failures, the name node is in charge of replicating nodes, whereas the data node is in charge of replicating blocks.
So the name node is in charge of noticing that there is an under replication based on the block reports. And when that happens, the name node is also in charge of instructing some other data nodes to create a new copy from another replica. This is what the name node's responsibility is. Creating new nodes, the name node cannot do it. You need humans, because to create new nodes, you need to create them, right? You need to physically put the machines in the cluster and or to create the virtual machines. So to some extent, it's also virtualized, right? If you have virtual machines, you can also create them, but this is outside of HDFS. This is on outside of HDFS that there are people who can add and remove the actual nodes. Does it clarify? Yes? Wonderful. Another question in here. Yes, go ahead. Yes, absolutely. The instructions are always, I'm repeating so that on Zoom they hear, the instructions given by the name node are always a response to a heartbeat. Yeah, always. It can never initiate a connection. It's always the data node that initiates the connection. All right? Is it clear? All right. And then the data transfer protocol, it's the actual blocks that can be transferred to and from the client to the data nodes. But of course, it would be inefficient if to create the 3 replicas, the client would connect 3 times to a data node to send the blocks when it writes a new file. So instead, we have what's called a pipeline, a replication pipeline, that the client connects to one data node together with a list of other data nodes that should have a copy. And then the data nodes create some replication pipeline, and then there is a flow of blocks like this from data node to data node, right? Just for writing, it's done that way. For reading, you just need one. Okay.
We have the data node. We keep the connection live the send data.
That's a good question. That I actually don't know. It's a physical detail. So it could be both. We'll try to investigate offline this. I actually don't know. There's 2 ways of doing that, right? Either you keep the connection open and send the heartbeats every 3 seconds, or you recreate a new connection every time. I don't know. In fact, the same thing was thought in HTTP, right? In the first version of HTTP, you recreated a new connection every time. And in the newer version of HTTP, you keep the connection open to do that. Yeah, I don't know. We need to look into it, and maybe we find an answer. All right. So what do we do on a metadata level when we communicate? We can create a directory, delete a directory, write a file, append to a file, read a file, delete a file. It's all the things you would also do locally. It's pretty similar on the level of HDFS, right? So this is meta operations. So now I have an animation for you that kind of put it all together. What happens if a client wants to read a file? So I'm assuming HDFS already has files, right? That we already wrote a few files. So the client is going to connect first to the name node. Exactly, this is where it starts. So it connects to the name node, asks for a file, saying, okay, I want to read that file. The name node looks at the namespace and so on and say, okay, yes, that file exists, that's fine. And here are the block IDs that are part of that file. And here are the block locations. I was even so kind as to sort them by proximity. Right? So the first block IDs I'm giving to you are the ones that are closer to you, and then they are sorted in descending, in ascending distance, right? I'll talk more about what metric we have for the distance, but this is right. So you start with the first ones that are closer, and if it doesn't work, go further. Then the client is going to request the blocks from the data nodes, and now it depends on the level at which you're looking at things. if you're looking at things from the protocol perspective, the client is actually going to connect to the data nodes one by one and request the blocks, always starting with the first data node in the list for each block. And then it's going to go through the blocks one by one, data node by data node. However, as you might imagine, as a user of HDFS, it would not be convenient if you have to implement it every time. So what happens is that there is a higher level library available in Java that takes care of it for you, right? It's all running on the client, but there is something called who knows the input streams, output streams in Java? Maybe some of you, right? So there is this abstraction that we can hide in the Java library on the client. It's some sort of driver that takes care of, fetching them from the appropriate data nodes. But to the user of the Java library on the client, it only seems like a single input stream that is a terabyte long, right? But this is all hidden. What's very important is to understand that this abstraction with the input stream is really a Java library running on the client. It's not part of the HDFS protocol. It's just a convenience on a higher level, right? Then that's it. And have 2 more minutes. To create a file, you say, I want to create a file. Then you get back the first block instruction. So here's your first block ID and the data nodes that should receive a copy. And then you organize the pipeline connecting to the first data node, and then the data nodes takes care of the pipeline. You send the data over, and then there is an acknowledgement that this will all receive. In fact, there's not just one acknowledgement. This is then the low-level network things. There is an acknowledgement every 64 kilobytes, and that's not even synchronous, meaning that you just ship your network packets on the wire, and you just get your acknowledgements asynchronously. And at the end, once you have the confirmation of all the network packets, this is really a network thing in there. The 64 kilobytes is not HDFS, that's network. And at the end, you have all of your acks, and then that's it. Then you get the next block, you send data, you repeat, right? Just like a repetition over the blocks. And that's it. And then you close, release the lock. Then there's all kinds of checks for minimal replication, and then it continues to replicate all the way to 3 asynchronously, right? And there's the final acknowledgements. All right. So I'm going to stop here for today. You can also read the textbook to make sure that you understand everything. As always, I would like to make sure that you followed. And of course, it's not quite working. I need to click again. All right, so let's see if you understood before it rings. 1 minute. Okay, that looks good. Okay, over 80%. Perfect. If you have any questions, make sure to ask them. Read again, read through the material, through the textbook. Don't forget to download the new version of the textbook because I added the Dynamo text to it yesterday. So don't forget to re-download it. Thank you very much. Enjoy the exercise session and see you next Tuesday. Thank you very much. Goodbye.